Also I thank you very much, Ankit, for this very, very kind words, too many words about me. And I really am very happy to be here at this very important conference. And also, I'm very happy that you are the organizer, that one of my former PhD students is so successful and active in its home country again. So I will talk today about climate meets complex systems. And this is usually my message. And I start to introduce or to ask people, are modern concepts of complex system science useful for earth sciences? This is a bit provocative question. Wait, was a bit too fast. But this is to start and to convince people. But you all know that since a few weeks, this all know now, and all are convinced, all would say yes, because now the next slide, because even the Nobel Prize Committee understood that climate is a part of physics, which was not always the case, by the way, and that complex systems is always part of physics, and especially the joining of both brings real progress. And here we have the three outstanding scientists who got the Nobel Prize exactly for this merging: Klaus Hasselmann, Giorgio Parisi, and Syukuro Manabe. And they really did pioneering works. Next, please. Bringing together complex physical systems, describing complex physical systems, and pioneering mathematical model of Earth's climate. And also very important, very early predicted that increasing levels of carbon dioxide in Earth's atmosphere would raise global temperatures. Let me go very shortly through some main achievements of them. First, to mention a bit more back, that the real breakthrough in all weather studies and weather forecasting was done by Louis Fry Richardson already in 1922, that's almost 100 years, 99 years ago, published the book Weather Prediction by Numerical Processes. And the main point is that he used physics equations for weather forecasts, not only statistical tools, but weather forecasts based on physics, on physical equations. But this was too early. It needed computers, as we know. Johann von Neumann was the first with his team to bring this to practice in 1950. But then a lot of progress has been made. But among all this progress, there was always a big problem understanding the underlying processes and also to describe deeply the reasons for climate change. And here are the pioneering contributions, especially by Hasselmann and Manabe. Let me start with Hasselmann. It's a great day today because he becomes 90 years old today. But he is very active. It's unbelievable how active he is. And he was director of the Max Planck Institute for Metrology. And he feels really as a physicist from the very beginning on, but of course also he applied physics. One very genius contribution by him was in the beginning of 70s when he developed a stochastic climate model. And this was very important that he described some elements, especially in the weather scale, as a stochastic part and not only as an average part, as was done so far. And this way he could explain the so-called red noise signals you got from the power spectra of all climate variables, of temperature, of precipitation, or whatever you wish. And this was not understandable at that time. But he could explain. Here are many engineers in the audience, and they all know what the red part of a power spectrum is. You have this also in climate, and he could explain. To give shortly a view into the equations. Next, what he did, he had then here a propagation and diffusion term, and the parameters Vi and Dij are time dependent. That's very important. And what he showed when he treated this model, that for on the climate range, also a bit longer term range, the predictability is very limited. And the maximum skill, from his viewpoint, is about 0.5. And this was really a very important, which is typical, we all know now for complex systems, but he found it already there and showed it in detail that you cannot become better in principle. And this was really a breakthrough, opened many doors. And next is one thing, he developed coupled models where he first coupled ocean atmosphere, later also biosphere in some sense, and also the chemical components he included. And then he studied with such models already in the late 80s, the influence of increasing CO2. Here are some scenarios. One is that you have double from the Z time state-of-the-art CO2. Then another is a reduced scenario D, also that politics, or we, better say we, not only politicians, we humans are reducing the CO2 output. And scenario 8 is what is called business as usual. That means increase again and again. And then he found in the next, as this was the input, then he used this model, and then he found that you really have, for a 100-year run, that you have a clear increase of the global mean temperature. You see from most lines of up to several degrees. Also you have this scenario A, this was a business as usual. He found that time 2.6 degree increase. But if you reduce the increase strongly, then you can strongly reduce the increase of temperature. But the main point is that he really could show that increasing CO2 causes an increase of the global temperature. And Manabe, I give only a few. Manabe, also about 90 years, I do not know exactly when his birthday may be. He is already or becomes soon. And he is Japanese, also Hasselmann German, and remains most time in Germany. Manabe is Japanese, made there, studied there and made PhD, but then went over to US and remains here in US, and also worked on models. Next, please, and studied especially the CO2 increase, the impact of the CO2 increase. And already in 67, by only an atmospheric model, I have to say, ocean was not included really, which is important, but he found nevertheless important insights. First, that at lower sphere in the atmosphere, also in the troposphere, which is important for our weather, for our daily life, you have an increase of the temperature if you have increasing CO2, but then a decrease of temperature when you are going to stratosphere and so on. And this was indeed, although the models were rather simple that time compared to the nowadays models, but this was found experimentally and by observations later. Also he really could show and could forecast typical behavior, which really happens. The next is then, he studied again CO2 and the influence mainly on the ice, on the thickness of the ice. And he showed that you have especially damages in the upper graph. You see the ice thickness, especially in the poles, are strongly expressed. And this is for the CO2 as it was that time, early 80s. And then he had 4 times increase for CO2 level. And this is shown for 1 year averaged. And you see that there is a strong decrease of the ice, what we observe these days a lot, that this is very heterogeneous over the season, especially in the Arctic. You see that in the summer months, from June, but more July till the early autumn, you have a strong decrease of the ice thickness. And this was shown with these rather simple tools, but this is what we observe these days. We observe it, of course, in more details, but this was the main finding he already made in the early 80s. And then he also studied change of the water circulation measured in Sverrups, which is a huge number, especially the fresh water circulation in the ocean. And you see here, when you have this S is a normal, unchanged CO2, and 4 times CO2, this is a lower curve, you see that the circulation is becoming less and less, and then you really have almost a stopping. There's a saturation at a very low level, and this is what we call these days tipping point. This was the first indication of a tipping point, that especially in the North Atlantic Ocean, the circulation could stop or could almost being stopped. And we have now, there was a strong debate about, but now very recently, there are strong experimental indications that this process has started. Fortunately, we are not at the tipping point, and we hope that we can avoid to get to reach the tipping point. Otherwise, it would be a disaster. And this is only to give you some glimpse about the really pioneering work of them. And now let me come a bit to my work. And this is also, I would mention one statement by Klaus Hasselmann. He was a member of the advisory board of a large EU project where we started applying climate networks. I will explain later what it is. This was new that time, and many people laughed about and thought, what are these crazy guys doing? But Hasselmann came to me at the end of all the presentation and told me, you should go ahead. This approach has much potential. This was 10 years ago. So now let me explain what it is. A climate network. This is a work with many people. Here are my group at PIC, but also many former PhD students, which are now around the world, as Ankit and Ugur, both were at this our special grant, our large school at University of Potsdam. Both were students there, but also, next slide please, many people from various countries which are experts in climate and related things, because you always need experts. I'm coming from physics. This is often not enough. You need also the local experts. So now let me come to the point. I will explain what climate networks means, and then give some idea how one can study extreme events. And this is our topic, hazards. Extreme events is related with hazards, and I will give you a few examples where our approach really works. We have system Earth. This is our main topic next. But when we talk about networks, you think about social networks also, where we have people, they are connected, and opinions are formed, etc., etc. But here in the system Earth, in the atmosphere especially, this is not a discrete system. It's a flow system, not people which act there. And therefore, we have to consider this more as a flow network. And what we try to do to look whether there is a backbone in this flow network underlying the climate network. With the help of this backbone, we try to describe some processes better and to get more information out via this approach. And one can also consider this as a kind of discretization, if you wish. And these partial differential equations, Navier-Stokes and related, have to be discretized. And we are doing here is a bit strange. Discretization, I would call it a more natural one, because when we start at the left upper corner, we have observational sites on the Earth, and we measure time series. Can be temperature, precipitation, density, whatever. And then we are looking for similarity or causality among the different regions. The different regions are our nodes now. And if there is a strong interrelation in the dynamics among the different regions, then we make a connection. This is the so-called adjacency matrix Aij. It becomes I1 if they are statistically significantly related, correlated, or there is some causality. Otherwise, it remains zero. And this is the way how we construct our network. You see in the middle, this is a type of network, and one can then use network measures to analyze this. So next, to show what can we do this way, we can infer rather easily teleconnections and long-range connections. And next, this is here, usually this is a movie, but you see also this projection, you see especially at the equator and here at the Atlantic Ocean, some rather long-range connections, and these we can infer rather easily this way. But we would like to go more for hazards for extreme events. Next, extreme events. And now I will cite another famous guy in physics, got, of course, also Nobel Prize. Test of science is its ability to predict. It's a very hard criterion, let me say. And let's see whether we can do it. And especially for forecasting weather and climate phenomena, it's a long-lasting challenge. And yes, I mentioned Richardson. These days, we have the very well-developed global circulation models, GCMs. They work very well, but the problem is the prediction horizon. It is maximum 2 weeks, not longer. And several extreme events are not predictable at all with these very sophisticated methods. Therefore, we thought, let's try to go via our climate networks. Next. Also can we go beyond 2 weeks in some cases? Okay, next. And for this first, we have developed a technique which we call event synchronization. I will shortly explain. We have here precipitation. Let's look for precipitation for strong rainfall, where the hazards could be floods or landslides, as we had in Germany very recently. And you see all what is above this threshold, the red line, are called strong events. These are the 10% strongest events. Then next slide, we look for the maxima. And now the crucial point is whether these maxima happen almost at the same time at different regions. And you see here 3 such guys remain, where we have synchronized, almost synchronized behavior in the occurrence of precipitation, of extreme precipitation. And if this happens, if such a synchronized behavior happens, not only one among 2 regions, but significantly often, then we make a connection between these 2 regions. And this is a bit different construction of networks, but it's more related for extreme events. So now again, go a bit faster through. Here we have 2 regions, and here we make this synchronization analysis. And if they are statistically significant, next now, then we make this adjacency matrix the same. We put a 1 among these 2 regions if there is such significant synchronization. And then we use network measures. Now, let's apply this approach. First, this was not our first, but I start with this because in some sense this was the most successful because this was published 2 years ago in Nature, and this was indeed the first paper in the journal Nature on climate networks at all, and we were really happy to get it. And we analyzed here strong rainfall data from satellite, from the TRIM satellite, which has a good resolution in space. Also in time, we use daily data, which is enough for this purpose. And we have then with this spatial resolution more than 500,000 grid cells. And that means we have to make, to construct this network, 10 to 11 comparisons. This is no problem for the computers these days, but the problem is a different one. It's a multiple comparison problem. It's a classic test problem, because if we have one time series at one region, we have to compare it with all the others, it's pairwise. That means we have to use this one data set again and again. And we are doing this with all the data sets. And due to this multiple use of data, some of the connections could become significant, although they are not. One has to make some corrections. There are classic corrections. They are too conservative. And the main part of our work in this Nature paper was to develop a method to identify really the real connection. There are pseudo connections, there are indirect connections. We only would like to have the direct connections. And here we generalized conditional causality and try to identify not only 2 adjacent regions or 2 regions at all, but identifying some bundles, because there must be a motion from region A to B, and we try to identify whether there is indeed a bundle. Then this is becoming significant. So next, now the result, you see on top, we consider here the region around of Himalaya and northern India and connected to all the other regions in the area of the trim data, plus minus 50 degrees. And you see on top, there are no corrections there. It looks like this area is connected to almost others. This is a bit too much. But after the correction, this is the lower figure, you see much less connections, and all what is shaded is has also not to be considered, is not significant. As we have much sparse connections, which is always good and looks promising. And we have also two kinds. The red are the more local connections, the blue, the longer one, the more teleconnections. So now let's make some statistics, not only from this northern India part, but from all the others, and pairwise looking for bundles. And what we find is then we calculate the probability, how often a bundle of a certain length, of a certain distance, maximum distance, exists. And we find then a decreasing probability, which makes sense. If you are going further away, then this probability becomes less. And this is log-log plot. That means it's almost linear here, by the way. But some people would call it power law, but I call it linear. But this goes till the distance 2,500 kilometers. And then, a bit surprisingly, we have again an increase. And the question is then, what is the reason that we have an increase when the distance is becoming longer? Next slide, please. And here it's really, we thought, and then we found that the shorter distances are due to regional weather systems, where the thermodynamics plays an important role of mechanism. And the longer ones are the teleconnections, which I mentioned before, and they are due to large-scale circulation dynamics patterns, as the Rossby waves and other ones. And this really induced a slight, not so strong, but some increase. That means there are becoming more connections when we are going further away. This is really, this makes sense, but this was interesting. So, and next slide, please. Then we thought, is there also can we find some geographically evolution of such strong events? And what we found is not only looking for the India, but also for others. We found a very interesting similarity to the so-called Silk Road pattern. This is a pattern going from west to east till eastern China and until Japan. And this, surprisingly, the strong rainfall events follow also, or have also such a characteristic as this Silk Road pattern. That means we have such a clear pattern. And this first shows that the Rossby waves play an important role in the creation, in the generation of such synchronized extreme events. And this opens also a door for forecasts. So next, I will give you, as the main result is these twofold behavior, regional weather system, teleconnection weather system. We also have long-range connections to even to America and to the southern hemisphere, new ways for prediction. So now examples. The first is India and the Indian summer monsoon. You all know, you in India much better than me. Although I was also often in India, I got my first Humboldt Research Award to going to India, and I was altogether I think more than 25 times in India. As I'm a good friend of India and know a lot. And the monsoon plays an important role in your life, that's clear. And especially next in agriculture, when you bring out the seed too early, no, this was too fast. To bring out it too early, as this farmer did, then all is drying out. You cannot earn anything. You cannot get plants out of this. If you bring it out too late, all is washed out. Also it is really so important to have a good prediction long enough, as long as possible. So we tried now with several data. Yeah, you can go ahead with the trim data again. Good. With the trim data, also we use the Aphrodite data, a very also almost real data, and we took then also some reanalysis data for temperature, wind, vorticity, etc. So what did we do? Next, please. we used 3 types of nonlinear approaches. First, we used this network approach and could identify this way the most sensitive regions, sensitive for the onset of Indian summer monsoon. That's important. And next, we use the so-called pre-bifurcational enhancement of fluctuation. That means if you are coming closer to a bifurcation or tipping point, and you always have noise in a natural system, then the noise becomes more and more amplified. Finally, some saturation. But from this amplification, one can already estimate the onset of this bifurcation. This we used. And finally, we used a very special property there on temperature and humidity. And what is, let me give the main message. What we could reach is that the prediction horizon for the onset of Indian summer monsoon is now about 40 days before the onset. This is much larger than it was before, and with a success rate of 74%. So now a bit more details about. And what we find as sensitive areas was also a bit surprised. This is North Pakistan and Eastern Ghats. And this is usually one looks for Kerala. That's correct, because the monsoon comes via Kerala. But the more sensitive areas are North Pakistan and Eastern Ghats. And this was a result of network approach. And then if you look to the right corner, lower corner, you see the variations, the fluctuations, the change of fluctuations in North Pakistan, Eastern Ghats, and averaged over whole India. And now next. Okay. No, that was one too much. So you see now the arrows where you see already early warning, especially in these 2 areas, that the fluctuations really are increasing. And this we used for the prediction. This is an important tool for the prediction. Next, please. And yeah, this is more technical. Next. And the question is then, this was 74% in hindcast, also looking into the past, how successful it can be. But then we did it from 2016 with real predictions, and fortunately they worked all till today. And every year we were successful with the onset. We are not successful with the intensity. We are working because you had in 18 and 20 very strong rainfalls in Kerala. And we are now strongly collaborating with corresponding institutes, especially in Pune, in India, in order to bring in our tool into their very well-developed forecasting techniques. And hopefully this will, together, we will get really success also for operational forecast. And so far it's not real operation. Next, please. Let me only mention where it also works. This was for the South American monsoon system, same data, but of course then the summer is there, December, January, February. And what we are looking for is extreme rainfall in Bolivia and these high plateaus. They cannot be forecasted at all so far. And they are really inducing hazards, floods and landslides. And next, I think we can, what we found then, we considered strong rainfall in the Buenos Aires area and found that it goes north-westwards till this area over Bolivia. This needed about 2 days with speed 80 kilometers per hour. That means in principle, one could forecast 2 days in advance such strong events. It's better than 0. But then the question was, why comes the precipitation from south to north? Because usually all is coming from north, from Amazonia. But then we looked and found an explanation, the mechanism, next slide please, that this is again due to Rossby waves, but Rossby waves coming from the Antarctica. Their cold fronts are coming and they are like carriers and really carry north-westwards the precipitation. So next, maybe only shortly to mention, but this is related very much to India again. These tropical cyclones are so important for extreme events, for floods, especially in India. And we found very recently with another new PhD student also from India. She is from Chennai originally. And we found that one could also follow up such cyclones with our network approach. And maybe the very final example, go a few ahead. This was tracking extreme rainfall during typhoons. This is especially important for Japan. This was also in our graduate colleague. And what we found then, next slide, please. The main result was that the landslide, most landslide in Japan, the distribution is more related to the extreme rainfall during June and July, and not during the tropical storm season, which is a bit later. This was surprising, and we hope that this also has potential for predictions. So, and now my summary, I hope, yeah. First, what is now well accepted after the Nobel Prize, climate is part of physics, also complex systems is part of physics, and their combination really opens new approaches. And next slide, please. I hope I could convince you that our rather new complex network approach is really powerful and helpful for some questions, not for solve all. We need the GCMs, we need all the other things, but especially for some extreme events, it seems to be very successful. But there are, next slide, many open points. I would say it's even in its infancy. We have to develop further methods. We have to make it faster. And also maybe methods of machine learning could be very successful. And my last slide is our publications on this. And with this, I would like to finish, and I'm open for questions, of course.